My name is Vetri, and my project was developing a real-time fall detection system for the elderly using thermal imaging and deep learning. And my research question was, is it possible to build an embedded system that uses deep learning to analyze thermal images for real-time fall detection? And the motivation for this project was that I kept hearing instances of elderly people falling and not getting help for hours or even days. And for example, my neighbor's mother fell and broke her hip and could not call for help. And only when she didn't show up to a meeting the next day did people realize that something was wrong and checked on her, and she had to be admitted to the hospital. And this is actually a big problem because over a quarter of the elderly population, or 12 million people, fall annually, and 29% of them live alone. But they need to get quick assistance because it can reduce their hospitalization rate by 26% and death rate by 80%. However, many individuals prefer not to wear medical alert systems or maybe unable to use them if injured after a fall, especially if they fall from something like a stroke. So my engineering goal, I set out some constraints and objectives that I want to meet, and then I designed my system based on that. And to do this, I used deep learning on an inexpensive Raspberry Pi microcomputer to analyze thermal images. And the component of a thermal camera met my constraints of maintaining privacy and working in the absence of light. And I used a Raspberry Pi because it's low cost and you can call for help, and allows for it to be a wall-mounted embedded system. And deep learning because it's high accuracy and robust for pattern recognition. And Python because it's easy to use and open source, allows the programs to be open source. So then I constructed the embedded system by wiring an 80 by 60 pixel FLIR thermal camera to the Raspberry Pi. And in the final product, it's inside a case and wall mounted, and the only cord it would need in functioning is a power source. So once I set that up, I collected thermal images to train the system. And for example, images where someone's standing, sitting, or two people standing are normal. And here someone's lying down in a sleeping region, so you need to classify that as normal. Since it's in a specific part of the image. And here's a non-human heat source, in this case, a dog. But this last image is classified as fallen because after someone falls, they'd be lying on the floor, but not in a specific region, like the bed region. So then it'd be classified as fallen. So to classify images, I used neural networks, which are the basis for deep learning. So the most basic one is a dense neural network where I just fed the pixel values into the neural network and transformed it from layer to layer and ended at an output layer corresponding to normal and fallen. But in a convolutional neural network, it first applies filters across an image to generate these feature maps that can be useful. So if someone's standing, there's more vertical edges when you apply a special filter than horizontal edges. So once you get those feature maps, then you feed it into a dense neural network and you get your classifications of normal and fallen. So to train neural networks, I use a database of thermal images and minimize the loss score, or how far away the predictions are from the target outputs. And I did that using gradient descent to update the weights and biases over time. And for results, I found that convolutional neural networks perform much better than dense neural networks and reached a validation accuracy of 1, while dense neural networks stayed at a low accuracy the whole training process. And that means that convolutional neural networks, when they reached an accuracy of 1, classified all 120 testing images correctly, which is pretty good. So then I want to test the optimal number of convolutional layers and convolutional filters and filter dimensions. And I found that 1 layer was optimal, and that 6 3x3 filters in that layer were optimal. And again, they classified all the images correctly. And I introduced factors such as a sleeping region and non-human heat sources, and found the accuracy declined on average to 98.8%, but not statistically significantly, which is good because I expected to actually decline further, since it's has to look at not only the fact that they're lying down, but what position they're in the image. And for the non-human heat source, it has to see that their heat signature is different from a human. And my last test was the number of training images and the number of pixels and how that affected accuracy. And I found that the minimum number of training images before that actually starts to decline is 50. And then the minimum number of pixels is 192 before that actually starts to decline. And that was useful because that tells me that I need at least a 16 by 12 thermal camera and 50 images to train the system. So finally, in real-time monitoring, a thermal image will be fed into a trained convolutional neural network. And if the fall score is above a threshold, the system would call for help. And it repeats this process every 10 seconds or so. And I wrote a program to carry this out in real time. And when a fall is detected, I use an API called Twilio to send a text message from the Raspberry Pi. In this case, it was Grandma may have fallen, please check on her. So in conclusion, deep learning was able to classify images with a high accuracy, even when accommodating challenging cases. And a minimum of 50 images at 16 by 12 resolution was necessary for a high accuracy. And this is actually a pretty low requirement, which makes it easy to use. And this system could potentially increase the safety and independence of elderly individuals living at home, in assisted living facilities, or in nursing homes. And most importantly, it's open source and publicly available on GitHub, all the details about it. And for future work, it can be used for many applications, such as monitoring the safety of autistic children at night. and currently the cost is $270. But if I used a lower cost Raspberry Pi model and a 32 by 24 thermal camera, which would be enough resolution, and that's $60, that would reduce the cost to $90, which is very affordable since it's the one-time cost. And I'd like to acknowledge my STEM teacher, Mr. Kerry James, and my science teacher, Dr. Barbara Stewart, and my parents for their support. And that concludes my presentation.
That was great. Thank you. I have two small questions. So you showed us, I think, 6 different examples of the types of images you needed for the training of the neural net. And then at the end, you said you needed 50 total for the accuracy. So is it 50 of each of those 6 scenarios, or 50 divided by 6?
Yeah, so I didn't have quite equal amounts of thermal images for each case, but I meant 50 images total. So I tried to have about an equal number of fallen images as I had the images that would be classified as normal.
Okay.
Yeah.
Great. And then, so we use FLIR thermal cameras in my lab too. They're pretty neat. But what happens if one of these people is wearing a snowsuit or a heavy winter coat in Maine? Does that mean you'd need to retrain your system if the intensity of the image isn't as warm?
Yeah, so this is also for indoor use, but if they're wearing something like that indoors, they wouldn't stand out as much in the image. And it's not on this poster, but I tried increasing and decreasing the contrast of the images. And I found that surprisingly, it doesn't significantly affect the accuracy when you use neural networks. So they wouldn't stand out from the background as much, but that shouldn't matter.
Okay. All right. Thank you.
So how does this work in terms of real time? Is it capturing a certain number of images per minute or several images an hour? What's sort of the timing of the image capture?
Yeah, so it captures an image about every 10 seconds or so, but that's just an arbitrary value. You don't need to capture images like very fast or anything. And when it does detect a fall, it sends a text message and then waits another minute before deciding whether to send another text message if they haven't gotten help, or like if they haven't gotten back to not being fallen anymore.
And would you have to, when you say that it has to learn from the images, presumably part of that is learning the space of the environment in terms of, like, if they're in a bedroom, then a lying position is normal. How much work needs to go into training the room itself as opposed to just the person in the room?
Yeah, so in my application, the way I implemented neural networks, you have to train it for the room that you're going to use it in. You can't train it in one location and use it in another, because you can see there's some background radiation that comes with the room. But I'm currently working on isolating the human image and drawing a box around them so that it can be trained in one location and it would still have a high accuracy in another location. And then it would also be easier to implement the bed region, because once you draw a box around the person, if that box overlaps with the bed region when they're lying down, it's still normal.
Great.
So that was a great presentation. Thank you. So I was wondering, so it was a similar question to what Christy had, and that was, do you have to do this dependent on the size of a person? Like if you have an extremely large person versus an average sized person, do you have to redevelop this system?
Yeah, so I haven't done too much extensive testing on training with one body type and testing on another. But when I tested it on myself, and then when I trained it with myself and then tested it on one of the family friends who has a different body type, the accuracy was still, I think, 95% on average, which is lower, but I think it's still pretty good.
In the current systems that are out there to detect falls and message and stuff are, really dependent on the person being able to activate, like a life alert or something. And so this obviously has advantages over that. But what about the cost? Have you done it like a cost comparison to the methods available now versus this system?
Yeah. So this is a one-time cost if you. So right now I used a higher resolution thermal camera because I wanted to do a study on what the lowest resolution could be, and I found that I could still use a 32 by 24 thermal camera and a lower cost Raspberry Pi model. And that would reduce the cost to $90, but it's a one-time cost. Whereas the life alert systems and stuff, even if the piece of equipment isn't as expensive, the monthly costs add up over time.
Right. Great presentation. Thank you.
I just have one other follow-up question. It seems like your evaluation of each image is as a static image. So it captures the image and then it evaluates the pixels within that image. Would it be possible to evaluate from image to image to look for motion? So a sudden fall or going from an upright position to a prone position or something of that nature, in which case that would indicate that the person has done something that is abnormal.
Yeah, so right now, the real-time fall detection takes an image every 10 seconds, but the thermal camera I'm using right now can take images really fast, like 20 times a second or something. But I was thinking, might as well try to keep it simple, because like you try to look at how fast they're falling on the ground. Like let's say they're just lying down slowly, then you might not want to call for help. But I feel like there might have been more ways to go wrong with that instead of just looking at their posture every 10 seconds.
Great. Thank you very much.